So now we're going to talk about inductors. And you've heard of inductors before, right? Inductors, I think, like everything else in electrical engineering, are very, very simple concepts that for some reason are taught in a way that makes it complicated, okay? But they're very, very simple, all right? And we'll explain what that is, and then we'll explain how they can be used in sensors, and we're gonna do that in an hour, okay? We're just gonna do that in an hour. Let's remember what we have so far, right? So far we have the resistor, symbolized by R, and the relationship between voltage and resistance is V is equal to IR. Great, right? We also had a capacitor, and the capacitor has a capacitance given by C, farads, typically microfarads, and its relationship, voltage across the capacitor, is I is equal to C dV dt. Right? There was this derivative introduced here, right? And you may say, I don't like capacitors. Maybe, but we couldn't have done filters without capacitors. To make a filter, you need to have a circuit that cares about frequency, and resistors don't care, right? Resistors are like, they're not picky, right? They let everything through, right? You know, like, you know those people, and you ask them, what do you want to do? You want to go to the arcade, you want to go to the beach, and they're like, whatever, right? That's like a resistor. They're not picky. But to make a filter, you need to have a component or components that are picky. And that's why without capacitors, we couldn't do filters. So we dealt with capacitors as sensors very briefly, but we certainly dealt with capacitors in their ability to make filters and to introduce this frequency dependence. And we'll revisit that a little bit, but that's why we did capacitors, right? Okay, resistors, capacitors, and then one more called the inductors. Okay, and inductors have just like you have a resistance, capacitors, they have an amount indicated by henries, and they have an equation which is V is equal to H di dt. Well, I guess we use capital I. Very similar, right? Just the V's and the I's have switched. They're both derivative dependent, but it's interesting that in one, the current tracks the change in voltage, another one, the voltage tracks the change in current. Okay? And of course, we have this differential form here. Now, as I've shown you in this class, we don't need to solve any differential equations because we have tricks that make us avoid solving the differential equations, right? And if you remember, what we did is we said, okay, let me use this. Resistors were kind of good. For capacitors, what we're going to do is we're kind of going to treat it like a resistor, right? We're going to treat it like a resistor, right? And we're going to call the resistance, right, 1 over JWC. Right? And once you do that, you can kind of treat it like a resistor again. So meaning in this other world that we lived in, V is equal to I times 1 over JWC. That's the trick we did. We wanted to make this into a resistor. We wanted to get rid of the differential. All right, and guess what? The same thing exists for a capacitor, where now we're going to replace the capacitor. You're just going to put a square around it, and you will write JWL. Oh, H. Oh, you know what? Why am I using H for henries? L is the normal symbol. So the units is H, but as I'll talk about, the relationship is given by L. So we're going to write JWL. And I'll explain that in a second. It's like I shouldn't have written farads here, right? I should have just written L for inductance here, okay? So for inductance. But the inductance is in henries, just like capacitance is in farads, and just like resistance is in ohms, okay? So we're going to use L as the standard symbol. And once we replace this with JWL, and we treat it like a resistance, well, JWL is just the resistance, right? And so we can write V is equal to I times JWL. And now we have done the same thing we did with capacitors, with inductors as we did with capacitors. We have effectively removed the differential, and now we can just treat them like resistors. And just a small point here, which will come up later, is that this here is also equal to I times minus J times 1 over WC. It's not how we normally did it, but it's going to come up later, right? Because I can multiply top and bottom by J to get a J, but then this J times J gives me my negative, right? So I times negative J times 1 over WC is the same thing here, right? But notice that I wanted to get both the J's here. And you want to notice here that there's a negative here and there isn't a negative here, and that ends up being very important as we get through it, okay? That's inductors. So now you're giving a circuit, right? Let's look at a circuit with inductors in it. So we're going to start with a circuit that looks like this. And we're going to have a resistor. We're going to have an inductor. Voltage. This has a resistance. Here's our inductance. And I want to know what the voltage is here. And the input is a sinusoid. And we go back to our sinusoids because, as I hope I've sort of started to make clear now, there's a value in thinking about things in terms of sinusoids, even if things are more complicated than sinusoids. All right, you're given this problem, you have to solve it, right? What are we going to do? Well, you could do this. You could say, well, I have a voltage here, and I have a voltage here, right? So you could say, oh, let's call this V in. You could say V in is equal to and there's a current, right, flowing through the circuit, I. We're not going to do what I'm about to do, but this is how you could do it, right? You could say this, so okay, this voltage here is going to be I times R, and there's going to be another voltage here, which is going to be equal to this, L di dt. And in fact, V in is, let's be specific here, is equal to A cosine of WT. So this is that. And you have yourself a little differential equation to solve. And some of you may say, oh, I think I could do that, in fact, right? I think I know how to do that. But another alternative approach here, right, which is to replace this with a resistor to solve any differential equations. And the way that approach would work is we would draw a box over this and say this is now a resistor with the value of JWL. So we replace that with a resistor with a value of JWL. Well, now it's just a voltage divider, right? There's a resistor here. Sure, it has an imaginary value with it, but it's a resistor. And there's a resistor here, and there's an input here. And we know how to do voltage dividers, hopefully at this point, right? A voltage divider would have the equation that, well, V out is going to equal, and if you want, I'll draw it like as this. Whatever this resistor is, right? if this was a resistor times Vn. Right, if this is a voltage divider, it would be this resistance over this resistance plus that resistance. And we have this resistance, even though it looks odd. We have this resistance, right? So we're going to take this, and we'll plug it into there. We're going to write where the square is. JWL and JWL. And this thing here has a fancy name, which is called the transfer function, okay? Because it multiplies the input to give you the output. And this should feel very much like what we did with capacitors, right? If you go back and look at the stuff we did with capacitors, exactly the same. The only difference was there were C's here instead of L's, but C's are just numbers like 3, and L's are also just numbers like 4. So there's nothing new here. And so this is the general approach of how you would solve circuits using sinusoidal steady-state analysis with capacitors. And there's some additional steps you have to take here, and I don't want to go through them now because they're the same steps you did before, right? If you remember, that step is really, this is in this form of A plus BJ, and you need to convert it to this C form, right, by separating it out the real imaginary, all right? Hopefully that rings some bells a little bit because we did it before, yes? So now you know how to deal with inductors. And now I should also flag up something. The approach I gave you to solve these circuits is like I would call it like the easy way. It gives you the correct answer, but it's the easy way. But I do sometimes like avoid, like little messy details, right? But for example, I want to note that this is true, but technically this would sort of be in a different, this input and output would also have to be temporarily represented in a different form, okay? I've also left out phase all the time, right? We never talk about phase, but there's a phase thing happening as well. So I've given you an approach that gives you the correct answer. It lets you derive these things. But I didn't get into detail. We can get into some of these details if you want, like why is this, where does this even come from, right? There's some mathematics there, but I just told you how to solve it. Okay. Now you may say, yeah, I don't need it. I actually could have solved this, right? I could have done it in one step. I know enough about ordinary differential equations. I could have guessed what this is. It's going to be, the answer is going to be cosine of something, right? And I think I can get it, all right? Sure. But what about this circuit? Again, it's a sinusoid. I'm going to have here an inductor, a capacitor. So C, here's my L, and I want to know the voltage here. And this again is some sinusoid, cosine of WT. And we're going to talk a little bit about this circuit because there's something very interesting about it, all right? But from a circuits problem, saying we'll solve it, right? Well, let's do it. Let's write out the equations, and then let's do it my way, right? So to write out the equations, you sort of know that, if you remember, the voltages always have to add up to 0 as you go around the loops, right? Like you start with a certain voltage and you add, it always has to come back to where you started. It's like height. You go up and down, but you have to come back to where you started. So if you were to write that, you would say, okay, well, here I'm going up A cosine of WT, and then I'm going to go down these other amounts, which is going to be L di dt plus, and here I'm going to have to write 1 over C times the integral of I. All right? Because I integrate this side, I integrate this side. So this is sort of the alternative. I had to switch, to get the V, and you see what I did here, right? This is the equation for the voltage across a capacitor. So I had to add an integral here, Hey, you're the one who wanted to do it with differential equations. I said I could do it without differential equations. You want to do it with differential equations? There's differential equations. So you would have to now solve this. And maybe you've seen something like this before, right? You think, oh, I know how to do this. I would actually take the differential of this side and then the differential of that side. So this I would just become regular I. And this would become a second derivative, and this would become a first derivative, and then I would do cosine. I think I can extract this out, right? But what if I'd added another inductor here, right? So now I say, oh, really? So okay, I still know. I'll say, okay, how about this? And one more for good measure. Okay, do that one. So you could do it. Could do it differential equations. You'd have to write all these different, and these are, right, this is C1, this is C2, L1, L2, R1, R2. You could do it. I mean, you could do it. You could say, well, I'm going to first write like this voltage loop and that voltage loop. You know what I mean? Like all the stuff you did. And you'd get a lot of equations. You have to solve them all, right, simultaneously. And that's hard. But here's something that is not hard. Here's something that's not hard. If instead of this, I said, you know what? Let me draw it here. I'm going to give you this circuit. Right, and so now I'm going to call this R sub C, R sub 1. They're all resistors. R sub L, 2, R sub 2, R sub C2, R sub L. Hopefully you can see what I wrote here, right? But it's just a bunch of resistors, right? And I say, now I want you to solve for, oh, by the way, in this case, like what's this current here, right? What's this current? Or, I don't know, what's the voltage across this resistor, right? In fact, I think you could do this. Because this is not hard, and it doesn't require differential equations. What it requires is just two rules. One rule is how you combine resistors in series, and one is how you combine resistors in parallel, right? And so I'm not saying you can do this in your head, but you could say, okay, I'm going to replace these guys here, right, with a single resistor. That's RC1 plus RC2. I'll replace this with a single resistor. I have these two resistors in parallel, so I know that one, right? I'm just going to do, it's the multiple of this times that divided by the sum. And the point is that when you have resistors, there's nothing I can give you that you can't handle. Again, I could add more and more, and you'd become annoyed. But you could solve it. Are you with me on that? Like, do you remember enough about sort of circuits and resistors that when you first saw this in circuits, it was intimidating. But now looking back at it, these weren't the hard problems. Because anything you can do with resistors is easy because it is addition and multiplication. And those are good. And no one likes differential equations. I mean, like no one wakes up in the morning and says, oh, I'm so excited. Even engineers, right? I'm going to go to work. I can't wait to solve some nasty differential equation, right? If you do that, good for you. You're a mathematician, right? But we don't. So this we like because it's addition and multiplication, right? So that's like elementary school math, right? And this we don't like because imagine what this system of equations would look like, right? I don't know how, right? It would be very unpleasant. Good news. Don't need to do it. Because you have a hack that turns capacitors and inductors to act like resistors. You see the value of the hack? And once you do the hack, you don't need differential equations. You're back to algebra. Now, there is one catch. The catch is you have to deal with these J's, or some of those, someone asked me, why don't we use I's? Yeah, I think physicists use I's. I think J's you see in circuits sometimes. That's the catch. That's the price you pay. But I think complex number, like working with complex numbers like a plus b, j plus C times DJ, whatever that is still algebra, right? So whatever you need to do, even though you have to do some complex number stuff here, which we did a little review on, right? It's not as bad, in my opinion, as this. So that's why I'm teaching you this trick. And now, in fact, if you were to get this, you could solve it because you would substitute each one of these with a resistor. You would collapse the resistors together, right? And then at the end, you would just need to do this final step of converting from A plus BJ to C. Okay, that's the big picture idea. Let's do it for this problem right here. Okay. And once we do that, we are done with inductors. There's nothing else to do with inductors. That's it for inductors. See? 30 minutes. That's it. I mean, there is some new stuff, but if you were tracking what we did with capacitors, I didn't add anything new with inductors. I just said, but write this one instead of this one. Yes?
Can you explain how it affects other circuits? Because you said you'd explain that.
We will, yes. Now, it turns out that when we actually make filters, we tend not to make inductors because they mess with each other. And I will explain that as well. And that will, in fact, get us to how they're used as sensors. Yes?
Previously, when we had the capacitors with the resistor, the transfer equation changed when the relationship changed. So for the high pass or low pass.
Same thing here. I deleted it, but
The first example we did was the resistor, then the inductor. So when it's the inductor, then the resistor.
right, you have two, sorry, it's very messy. You have these two variations, or if you want to think about it, think of this as the input and that's the output. This is the input and that's the output. One of these is the high pass, one of these is the low pass. But guess what? It's the opposite position compared to the capacitors. And if you worked it out, you would see it. So there's this interesting symmetry between capacitors. And so you could make a high pass or a low pass using inductors. You would actually have to swap the position of the inductor because of that.
So the transfer equation would also be inverted. So for example, it would be.
Yeah, because look, just because of that, because of where they land. And so you'd actually end up, yes, they'd be inverted, but there'd be symmetry all the way through. Okay. Now I want to talk about this one. This is the only one we're going to talk about in a little bit of detail. And this one's fun. Because it relates to something that I want to say something about called resonance. And you've heard that word before. Did you do it at any classes? Did you see resonance in any class? Mechanical? Because it comes up. Huh? In statics, you talked about, and when did resonance come up in statics? Oh, bridges, and what happened? It's bad things can happen, right? What happens? They start to shake all of a sudden, and then they rip apart, right? Okay. Huh? An opera singer smashing cups, which is true. What is that? So I want to talk a little bit about that, because I think it's interesting. And I think it's yet another concept that's very simple, right? Because when you learn about it, I think you can be a little bit swamped in some of the math. There's usually like some sort of second order, right, differential equation, and you're not really sure what's happening. But here's what I want you to understand. Let's start with Emily, okay? So this is you. And I want you to give me something that resonates with you. Maybe it's like some art or some music or a movie or a person. Personally, like when you say, oh, this resonates with me, right? In that sense, what's something that resonates with you? Huh? Your pillow. Fine. So Emily got a pillow, and there's something about this pillow that resonates with Emily, right? When you're with your pillow, it does something. All right. So now, let's see. Adrian, what is something that resonates with you? Painting. Perfect. Okay, now we have painting. So painting, Adrian is saying, resonates with him, right? And he knows what that means, and you know what that means. It means that he stands in front of a certain painting, and he feels something inside of him, right? That is similar to what Emily feels with pillow, right? But here's what I want you to note. This is the key idea with resonance. While Adrian likes pillows, they don't resonate, and specifically Emily's pillow, they don't resonate with him in the same way. He says, yeah, I like pillows, I sleep on a pillow, but it doesn't do something to me the way that a painting does, right? Or the way this, like there's a song, and that's like, this is my song, right? And that resonates with you. So we all know what that means, right? And it turns out that Emily, right, while she's not opposed to fine art, right, paintings don't impact her in the same way. And so what I'm trying to illustrate here is there's two aspects to the resonance. There is the thing about the person, and then there's the thing that's being sort of applied, right? I'm using applied here. Applied to the person, right? It's the two together that create the resonance, right? So if these were whatever, one, you see what I'm saying? That's, when you think about resonance, you need to understand that the ability of something to produce a resonance inside of you, maybe it's another person, right? Maybe it's your boyfriend, right? I don't know, right? The ability that someone to do resonate inside of you, right? Maybe you really like your boyfriend, but like your friend really does not like your boyfriend, right? Because the boyfriend produces a resonance in you that does not happen in the other person. So the resonance, as we already understand it, it depends both on the thing that's acting, but it really also depends on us. You get that idea? And so you can't talk about resonance without talking about these two things together. The two have to happen, right? And that's true, for example, when an opera singer sings and they break a glass, right? There's two things, right? There's something about that glass. She's not smashing a coffee mug. She's smashing a mug. She's also singing at a very particular note. Or when those bridges collapse, right? Something happened. There was some sort of wind pattern. There was a very particular wind pattern, and then there was a very particular bridge structure. So that's resonance. Interesting, right? This circuit here has resonance. I'm going to show it to you. So now we're going to leave that little fantastic talk, which I enjoyed. My secret wish is to be like a poetry professor. And then all we would do, right, is we'd go out to the quad and we would sit under the trees, right, and watch the leaves and then, and talk about our feelings about the fall, and it'd be wonderful. But instead what's that? We could still do that. Maybe, okay, last day of class, maybe. What's that? You did that in bio? The professor took you out?
He was like, let's go out to architect building. He was like, look at the trees. How do the trees make you feel? That was Bio 229. I have no idea.
How do the trees make you? Okay. But here's the thing. Like we talk about. But what if resonance had, in an analogy, a mathematical or physics explanation? Well, that would be interesting, because we like to talk about resonance. But you tell me there's an equation for Emily and her pillow, and for Adrian and the paintings? Not exactly, but I'm going to show you that there is an understanding in physics and in circuits of a similar phenomenon called resonance. And it's going to be very easy to see, okay? Because what we're going to do is we're going to solve the circuit. And we're going to see what's going to happen here. Now, here's the thing we're putting in, right? This is like Emily's pillow. And this is the thing that's responding. Let's talk about, here's Emily right here. But Emily is the inductor. Emily is this whole system. I'm interested maybe in the voltage right here, but Emily's the system, right? So we have the same analogy. Let's solve this. So what we're going to do is we're going to do this, like what we always do. We want to create this. We want to turn both the inductor and the capacitor into resistor-like elements. And we know how to do that, right? We just, where we had the C, let me do orange, I think it's working. Where we have the C, I'm going to, orange. I'm going to write 1 over JWC. This is now my resistor. And where I have an inductor, right, this is the new thing that we learned today, I'm going to write JWL. And at this point, I can treat it like a resistor. It's like Ohm's law. And so in one step, we have our answer, which is that V out is going to equal to V in times, so I'm going to say 1 over JWC over, I'll write it out, JWL plus 1 over JWC, but I'm going to rewrite this. I'm just going to do one little thing, 1 over JWC. I'm going to rewrite this as, I'm going to take this J, I'm going to put a negative here, minus J. Remember I said I could do that here? Okay? So I just want to put, I want to get the J up here because that allows me to pull the J out and write WL minus 1 over WC. Right? So this is the relationship, right, between the pillow, sorry, this is the pillow, and this is Emily, and this is Emily's response to the pillow, right? So this 1 over JWC, let's see clear, over in here, this is J times WL minus 1 over WC. It's all algebra so far. And yes. What? Let's get out of this orange thing. I'm not going to. Okay, but I'll switch to the purple. Okay. There's a bit going on here, but I actually, and in fact, you notice this J is going to address this J here for us as well, all right? But I want to focus on this term here, this WL minus 1 over WC. I just want to look at that term. I know that this, whatever this is, right, is going to amplify the input to give the output. So I want to look at WL minus 1 over WC. I want to look at this term. And I'm curious if this term could ever be 0. Right? Could it be 0? Could any conditions make it 0? And this is how we're going to get, yes?
Sorry, why is it minus and not plus?
Because this minus J over 1 over WC, I pulled out the J. I pulled out the, and it is important that I get this minus here. Okay, it is important. You'll see where I'm going in a second. So what I'm going to say here is this is the same thing as WL equals 1 over WC, or in fact, W squared is equal to 1 over LC, or W is equal to the square root of 1 over LC. So I'm trying to say this, if the frequency happened to be the square root of 1 over LC, now what does that mean? If L was 2 and C was 1, right, then WC would be 1 over the square root of 2. This is just a number, right? So I'm not saying that you're saying, but why is the frequency high? I'm just saying, what if it happened to be? Just so happened that the frequency you were putting in, the pillow, as it were, right, happened to have this frequency. And then we drove it into the system. It happened to do that. Then what would happen? Well, then this term here becomes 0. 0 times J is still 0, right? Something divided by 0 is a huge number. And so in this situation, V out becomes a very, very large number. In theory, it goes to infinity. Practice, it won't, right? In practice, it won't. But in theory, yeah. In theory, this V0 can become huge. Now that's interesting because when we talked about voltage divider before, we said, well, you have a voltage, let's say 10, and you can divide it 8 and 2, 1 and 9, 5 and 5. But you could never get more than what you put in. But now you can. Now I can have here 10 times the cosine of WT, but I could have here 1,000 or 1,000,000 volts. How interesting that this system here is actually what it's doing is it's sucking energy in and it's storing energy inside of itself, right? And there's some interesting things happening here with this capacitor playing with this inductor, and they're passing energy back and forth. But the net result is that the voltage blows up. And that's resonance. And what I want you to understand is that resonance comes from the fact that you have a match between something about the system, right? This is Emily, this is pre-pillow, right? There's something about the system and something that we put into the system, and if those things happen to match, if the system has this sort of natural preference, if you want to say, for something, and we give that to the system, these very unusual things start to happen that sometimes are undesired, like bridges collapse, and sometimes are desired, right, when we want to produce these resonant phenomenon. Does that make sense? And this I couldn't have talked about this until we had inductors, because there's no circuit I could have given you with resistors or capacitors on their own that would have done this. I needed to throw in an inductor. This is the simplest circuit that will do it. I needed to throw it in. I needed an equation that looked like this, right? And maybe, I don't know, maybe in differential equations you would do stuff like this, like you would set this to 0. I don't know, maybe something like this existed before for you, okay? But now you know what to look for when people talk about resonance. Interesting, okay? I think it's interesting. Finally, now we're done with inductors, and we're done with inductor circuits, yeah.
So, what does that do for us, though? Like, what's the benefit of using an inductor?
We're not going to use this in this class. There is no application in this class. Obviously, you could use this to create larger voltages that you usually have to work with. This is not a circuit we're going to use in this class. The reason I wanted to introduce this circuit is I wanted to show you that when you have capacitors and inductors together, you need to be aware and perhaps concerned about these types of situations, right, arising. And people do use, I mean, there's also stuff with RLC circuits and so on. So because I wanted to introduce inductors and I wanted to show you how to use inductors in circuits, I needed to cover this concept as well, okay, which comes up when you have inductors and capacitors. But in this class, we're not going to be building filters out of inductors for the reasons I'm about to present now. In fact, I don't think we're going to use inductors at all.
But are they used like in medical devices? Or are they typically used in other devices? Like what kind of device would need an inductor?
So let's talk about that. For example, a transformer. So something that takes high power line voltages, we'll talk about why, and produces lower power line voltages, uses inductors. You can use inductors for, if you have an implant, a medical device, and you want to charge it externally, you could use inductive charging. So there are applications. Those are some of them that come to mind, but none that we will be using in this class. Yeah.
So when you have a phone and you put it on like wireless charging, does that use inductors?
There is a type of inductive charging. I don't actually know if our current phones, if that's what they use. I'm assuming maybe that's what they use. They use inductive charging. And so let's talk about. So now we're going to talk about inductors as physical objects, and we will understand how that works as well as a result of it. So let's talk about inductors as physical objects, and that part of it will become clear as well. Okay. So let's talk about inductive sensors. And here the story is very similar to resistive capacitors and so on. When we did resistive sensors, right, I said I want you to think of a resistor as a physical object whose resistance is a function of its resistivity, which is something that it's made out of, and its length, and its area. Right? And therefore, if any of these change, you have a resistive sensor. For example, if temperature changes resistivity, this will change. If we stretch it, like it's a strain gauge, and these change, it will also change, right? Remember. Then I said capacitor drawing small here, is also a physical object equal to something related to what's inside of it times the area over the distance between the plates. And if we think normally when we grab a capacitor, we don't, just like normally we don't want a resistor change, we don't want a capacitor change. But if we had a capacitor where its plates were moving or something like that, or the material between them was changing, lo and behold, it's a sensor. Same thing for inductors, okay? Now we have an inductor. Inductor is a physical object. It is a loop of wire. And sometimes there is something inside the wire, and the inductance is given by N squared G U. Okay. And what N is the number of loops, because you'll notice it isn't one loop, it's several loops, right? G is a geometric factor that includes other things like how tight these loops are, how big the loops are, right? It's a geometric factor related to that. And U is a property of the material specifically that is inside the loop. Same thing, right? That's what I told you, like same thing over and over again. It's like the same song, different versions of it. And so what makes an inductive sensor? Well, if any of these would change, right, then it would all of a sudden become a sensor. So for example, I'm going to draw it this way. If there is some, make this clear. Let's say there's some object and is moving delta x. It's moving in and out of this inductor, right? So it's changing what's inside of it, then its inductance would change. And so now, if for some reason this is how you wanted to measure displacement, you could measure displacement. And again, I'm really strained to think of examples where inductors are used in this way, right? You can imagine, well, what if this is a function of temperature? Yeah, in principle, yeah, but I'm not aware of that being used. And so we haven't spent too much time on this. But now we've completed the whole circle, right? Resistive sensors, capacitive sensors, inductive sensors. They're physical objects with relatively simple equations that have both geometric terms, right, and material property terms. That's all you need to know about inductive sensors. Okay? But we do need to talk about this one other thing that does come up with inductors, when you keep asking, which is how they talk to one another. Okay? So let's talk about that a little bit. There are certain physical principles, right, that make the resistor act the way it does, and makes the capacitor act the way it does, and makes the inductor act the way it does. And we haven't spent too much time on what's a resistance and what's a. Well, let's talk a little bit of what it means. How does actually an inductor work? So there is current that is flowing down this wire. Right, it's wrapping around and around, then eventually it comes out, right? As the current flows through the wire, it generates a magnetic field. There's a new term for you, magnetic field. And that magnetic field looks like this. It's inside it, but it spills out of it as well. Okay. And this is because of some physical property called Ampere's law, but there is now a magnetic field that is present inside of it. And it turns out that the presence of the magnetic field generates a voltage across it through another law called Faraday's law. Okay, so there's some physics going on here where the current flow generates a magnetic field, and now you have a magnetic field, and it turns out that a loop, right, in a magnetic field will get a voltage on it. And I don't want to spend, I mean, we can get into more if you want to. And by the way, why are there multiple loops? Well, one loop will generate 1 unit of magnetic field, but when you have 2 loops, it doubles. Okay? And so you have multiple loops, you generate more of a magnetic field. All right? But it also turns out that the voltage doubles because now you have a magnetic field in one loop, so let's say that makes 1 volt, but then you have another magnetic field in another loop, makes 2 volts, and another magnetic field in another loop makes 3 volts. So n squared, because we get 2 benefits from it. The first is in the generation, and the second one is in the transduction, all right? And that's maybe more physics than we need here. And I mean, something about magnetic fields. We don't. I feel like it's a little hard to get intuition about what a magnetic field is, right? I guess it's a picture of it, right? And the reason it's a little bit hard is that we don't see magnetic fields. We don't feel magnetic fields, right? So it's a bit like, what is this magnetic field that we're talking about? Is it even real? Right? What does it mean? I think it's all right to just to not be comfortable with this and just say it's a magnetic field is just an idea that people created in order to help us explain certain things. It's like we talked about imaginary numbers and how they're not real, right? They're not. There's no but actually there's no even numbers at all, right? But these are made-up concepts, and imaginary numbers are made-up concepts. Magnetic fields, I think, is a step beyond it. It's like well, you are somewhat intuitive. You are familiar with force, right? Like force is, you don't go out in the street and say there's a force, but you know there are forces out there, right? Because you can see this happening, right? You see that it's moving something, right? So you know there must be a force, right? If I drop it, I don't want to drop this, I'll drop that, right? You know that there was another force acting that pulled it down. And so we know the force is there because it moves things, right? And magnetic fields, we know they're there because they move things, like motors, Teslas, right? Are situations where a magnetic field results in a motion. All right, so there is something here. There's something here. It's a concept of magnetic field, and so it's intuitive as what it is, and it's important. And the reason why am I talking about this in detail? We didn't get into this with capacitors and that, because this is what can happen. And the question is, what is the relationship between the current that's flowing through here and the resulting voltage? It's this. That's the relationship. So if you want to ignore everything else, just ignore everything else and just say, I'll rewrite it here, that the voltage is equal to some number, everything comes together, right? Some number here, all these things, times the change in current over change in time. Why a change? Because that's what Faraday's law of induction says. It says that the magnetic field has to change to produce a voltage, and so this is the relationship. Okay. The issue or the opportunity comes up when there is another loop of wire here. So this guy's just hanging out, minding his own business, all right? But he's hanging out next to this one. What's going to happen is that some of this magnetic field will pass through him, right? Now, if you want, I could have actually drawn this. I could have brought this in so that they were overlapping. right? I could have done that, and then it would have been the same magnetic field, right? But it would have been harder to see, so I shifted him out here. But you can see that at some distance, how much? Well, it's going to be not the full dose, but it's going to be some fraction of it. And the closer he is, the more he's going to pick up. So now there's a magnetic field. He didn't generate it, but he's picking it up. Well, now the second rule applies, which is that we're now going to get, now we're going to call this voltage 1. Now we get another voltage, voltage 2. This one gets a voltage because it's experiencing a magnetic field generated by this one. So you can see how now it has jumped in space, right? There's no physical connection here. There's no physical connection here, right? That's why you can use it for charging, right? There's no physical connection, but the magnetic field goes from here to here. So if this is the source, right? And here we have the thing receiving it, right? Your charger, and right, it could be a charger for a pacemaker on the outside. And here you have the coil on the inside picking up the voltage, and maybe that's connected to a battery or to something else. Now the voltage here is given by this equation, M di dt, where this is called the mutual inductance. So it is not more complicated than this equation, all right? But these terms here have changed, right? I mean, for example, the farther away this is, right, the lower the mutual inductance will be. In fact, if I were to put this coil in the same position, right, you actually ask what the mutual inductance would be, right? And there's something interesting happens. You see how this depends on loops? So I want you to imagine, this is the final thing we'll finish. Okay, I want you to imagine that this one had 10 loops, right? This one had 10 loops that was generating it, right? And so it had 10 loops, and the voltage it gets is 10 times 10, right? Now this one here, right, has 100 loops, and I bring him in. What's his voltage? 10 for the generation, but 100 for the receiving. So 1,000, right? So 1,000. Meaning the number, if this has a different number of loops than this, then this voltage is going to be proportionally different than that. That's how transformers work. That's how you can step voltage up or down. But it has to do with the ratio of the number of loops, which we don't really deal with transformers here, okay? But if you want to know one thing they're useful for, that's one thing they're useful for all the time, right? Is how we can, if power is transmitted at whatever it is, thousands of volts, and here it's hundreds of volts, how do you step down that voltage? Transformers. Yeah.
So would that be analogous to gain?
You could think of it as a gain, yeah, from one side to the other, right? So the voltage, in the example I said, right, there would be a gain on the voltage. You would actually be able to step up the voltage by a factor of 10 just by having 10 times more loops. 10 times more loops here, right? I mean, again, you want to put them right next to each other. So, but this is also a problem because now you can say, wait, I built a circuit, I built a filter, and I put an inductor here, and then I put an inductor here. Wait a second. Now what's going on, right? So all this, everything starts to break down, right? Because you have a circuit. Maybe there's one inductor and then another resistor. I don't know. There's another inductor here. And you're trying to figure out what the circuit does using my rules, but you don't expect this one to talk to this one. Or what if there's a completely different circuit here, right? Like another circuit, but now suddenly you can see the problems, right, that relate when we're using these inductors, right? They're like little antennas communicating with one another when we don't necessarily want them. That issue does not exist with capacitors, right? Whatever capacitors do is restricted within its plates. So it's a local phenomenon. So that's where we don't, that's one practical reason why we're not building filters out of inductors for exactly this reason. But then there are situations where people use this on purpose, right? There is, for example, a situation, I won't go back to this awkward situation. Let's say you had a rod here, and that rod was moving up and down. that would end up changing the mutual inductance. It would change the material properties between these. And so how much voltage you picked up here would vary. There's a name for that, in fact. I think it's called an LVDT, like a linear variable differential transformer. But again, I do not know why you would use that in biomedical instrumentation. Yes? We'll get to MRIs and imaging, and there are magnetic fields there, so we'll get to imaging at the end. And so there is something else going on there, which is a little bit more complicated than this. We're going to move on to, I don't want to avoid the question, we're going to move on to pulse oximeters, which I think are going to be very interesting, right? Which send light, and that will then set us up to understand sort of broader imaging techniques as well.